In this lecture, we're going to try and come up with an example that tries to drive the point home how or why you would use partial ordering for your three-way comparison operator. Suppose we are implementing a point class, and for some reason, we can only compare points that live within this range here. We can compare points only if x is less than 100. This is the x-axis here. We have our y-axis. And we can only compare points whose x is less than 100, y is less than 100, and we have the same constraints on the negative side. So x needs to be greater than minus 100, and y needs to be greater than minus 100. If our point is within this range, we can compare it to other points. But if it falls outside this range, we can't compare it with other points. And suppose we have a physical limitation that prevents us to be able to do this for whatever kind of problem we are trying to solve with C++. So these are our constraints here. And we can model this using partial ordering, in that any point that falls outside our valid range is not going to be comparable to other points, but all the other points are going to be comparable. And we are going to be comparing the points based on the length. So it is going to be the same length we have been using all along. We're going to be comparing the distance from our current point to the origin of our Cartesian coordinate here. So suppose we have a y-axis and we have an x-axis here. So a point that is further from the origin is going to be considered greater. This is the design we want here. If we have a point here and we have another point, for example here, the one which is further from our origin is going to be greater than the one which is not further from our origin here. So we're going to be using the length to decide if a point is greater than another one. Here we have a simple implementation of how we could enforce our range. We could enforce that our points live within the 100 distance from the origin, and we're going to set up a function or a member function which is going to do that. The function is called isWithinBounds. We're going to pass a point to it, and we are going to compute the absolute value of the coordinate. So we're going to consider the x coordinate and see if the absolute value is less than 100. We're also going to see if the absolute value of the y coordinates is less than 100. If all these are true, we're going to return true to mean that the point is within the bounds. And if this returns true, we will know that our point is comparable to other points because it's living within the valid bounds of our comparisons here. If this is not the case, we're going to return false, and we know that somehow the point is going to be living outside our possible range here, and we can't compare this point to other points. So this is the main purpose of this member function here. So once we have this set up, we can set up our class to do what we want. So we're going to set up a three-way comparison operator. And the first thing the three-way comparison operator is going to do is to check if the point is within bounds. And we're going to look at the current point, and we're going to look at the other point that we want to compare to. If they are both within bounds, we know that we can compare them. So if the left operand is greater than the other one in terms of length, we're going to return partial ordering greater. If the left operand is less than what we have to the right in terms of length, we're going to return std partial ordering less. And if neither of these is true, we're going to know that they are equivalent. If the points are not within our bounds, we're going to return unordered to mean that one of these points is not comparable to other points. Notice that the first decision we needed to make was the kind of comparison we want to do. So here we are doing partial ordering. We're going to return that here. And because we have a custom three-way comparison operator, we are also going to put in an equals operator, which is going to compare based on the length. And this is what we are doing here. Once we have these operators in, we will be able to compare our points. This is going to work like we want. Notice that for point 1, we have 101. So this is not going to be comparable to other points because it is outside the range that we can compare to other points. So this is going to give us something interesting to look at when we run the code in a minute in Visual Studio Code. But if the points happen to be within our range of 100, we're going to compare them without a problem. And you see that we can use all our operators here. And this is really cool. Now that you know this, we're going to head over to Visual Studio Code and play with this a little more. Okay, so here we are in our working folder. The current project is zooming on partial ordering. We're going to do an example of this. We're going to grab our template files and we're going to put them in place. And we are going to open this in Visual Studio Code. Let's do that by dragging and dropping here. This is going to give us our main CPP file. We can clean it up a little bit and remove what we don't need. We can close the left sidebar here. And I am going to put in the code and try to explain this because I don't want to waste your time watching me type all this. So we're going to have a point which is going to be wrapping around two member variables, mx and my. And we're going to make them integers. And we're going to set up our function to see if our point is within the bounds that we support here. So we're going to see if the absolute value is less than 100, both for x and y for this point. And if that's the case, we're going to return true. The point is going to be within our comparable range. And if this is not the case, we're going to return false to mean that the point is outside of our comparable range. We are also using the square root function, so we should include CMath, which is the library where this thing lives. So we're going to say CMath here. And after we have our is within bounds function, we can use it in our three-way comparison operator. If both our points are within bounds, we're going to do regular comparison. And if the left operand is greater in terms of length, we're going to say partial ordering greater. If the left operand is less than the right operand in terms of length, we're going to say std partial ordering less. This is what we're going to return. And if neither of these are the case, we're going to return std partial ordering equivalent to say that these guys are equivalent. But if either of our points is not within our comparable range, we're going to say that one of the points is not comparable to others by returning std partial ordering unordered. And I really needed to do this example here because this is the first case where our ordering is not decided by the type of our member variables. Our ordering now is decided by the range of the values that we support that we can compare to other values. And again, as I said in the slides, this may be a physical limitation, for example, imposed by the kind of problem you are trying to solve, and you might only be able to compare things that are constrained within this range of 100 and 100 for the absolute value of the distance to the origin. And this is a possible solution of how we could do that using partial ordering here. Once we have our three-way comparison operator, we will also need an equals operator. We are going to need to put this in ourselves because the moment we put in our three-way comparison operator, the compiler is no longer going to give us an equals operator. So we put that in, but it is not complicated. We are just going to compare the lengths of our points. And if they are equal, we're going to return true. If they are not, we're going to return false here. Once we have our code in place, we're going to play with it in the main function. We're going to set up 2 points first. Let's make sure the first point is in bounds because I want you to see that everything is going to work as long as our points live within the range that we support for comparison. We're going to try and build this, and notice that we are using all the operators. We have greater than, greater or equal. We really have all the operators. We even have equals and not equals. Let's build and see that this is actually going to build. We're going to use GCC here. The build is going to be good. We can bring up a PowerShell window that we can use to run this program. We're going to call Rooster, and we're going to see that based on the length information, 0.1 greater than 0.2 is going to be false. Let's put in 10, 10 and 20, 20 because that's going to be easy to follow. Let's do that and say 20 here. And I think we can also put in, we don't need to put in an output stream operator because that's really overkill for what we want to do here. I think it is clear enough that 0.2 is going to be further from the origin than 0.1 here. So let's build and use GCC to do that. The build is good, we can clear and run Rooster. So 0.1 greater than 0.2, this is going to be false because obviously 0.2 is further away from the origin than 0.1. 0.1 greater or equal to 0.2, this is going to be false. 0.1 equals to 0.2, this is going to be false. 0.1 is not equal to 0.2, this is going to be true. 0.1 is less than 0.2, this is going to be true. 0.1 is less or equal to 0.2, this is going to be true. But the moment we put in a point which is going to be outside our comparable range, let's put in 110 and 110, we can do that. We're going to see that all the comparison with this point are going to be off somehow. They are always going to return false because we can't really compare to this point, which is outside our comparable range. And this is really cool. We're going to see that in a minute when we run our code. So let's build and run. The build is good. We can clear and run Rooster. Now we're going to see 0.1 greater than 0.2. This is going to be false, but we know that 0.1 is obviously further from the origin than 0.2 here. If we try to plot this, we can put in our y-axis, we can put in an x-axis. So 0.1 may be somewhere like here, 10, 10, and 0.2 is at 110, so it is further away from the origin than the point that we have here. But this is not going to matter because this point lies outside our comparable range, which might be something like this. So what the compiler is saying, I can't compare the point I have here to the point that is outside my comparable range. So I can't really tell you if it is greater or less than any other point because I can't compare to it. And we achieve this using partial ordering in our code. So greater than 2.2, this is going to be false. Basically, any kind of comparison we will want to do with 0.1 is going to return false because our computer can't really compare to that point, which we can't compare to in the first place. This is the design we wanted to achieve here. This is really all I wanted you to see in this lecture, a possible case where you might need to do partial ordering in your design. I hope this is super clear. If you have any question, you can ask. I will do the best I can to help you out. We are going to stop here in this lecture. In the next one, we're going to try and sum up on how in practice you're going to use your three-way comparison operator or comparison operators in general in C++ 20. Go ahead and finish up here and meet me there.